got some cool stuff to talk about. We're going to talk a little physics today. Start talking a little physics. So we've talked about continuity. We've talked about intermediate value theorem. Now we're going to take a look at how this applies, how we apply this to actual calculus. Okay, so this really starts like in our textbook. This would start Unit 2. And I'll kind of lump in the stuff on continuity with this stuff we're doing right now. So we'll do a little in terms of like if you wonder when the next test is coming up, relatively soon. We'll kind of introduce this idea, the stuff we're talking about today, and practice a little bit, and then we'll do a test over just a little less material this time, a little shorter section. Okay, so one issue I wanted to address because I felt like I kind of glossed over this last week. Brackets or parentheses for the intermediate value theorem, right? I told you guys, parentheses really make more sense. And which one is right? Well, you could use either one. It just depends on the context. If we say f is continuous on the closed interval from a to b, if we think about what, the intermediate value theorem, if f of a is not equal to f of b, and k is an intermediate value, it's a value between f of a and f of b, then what does the intermediate value theorem guarantee? At least one number between a and b or including a and b. Can anybody tell me what the difference is in how we define f that determines whether we include the endpoints or not? Any suggestions? And let's think in terms of our picture. I don't want to spend a ton of time on this, but it's an interesting point. So here's our intermediate value theorem picture, right? We've got some graph, call it f, and we know that at a, the value of the function is f of a, and out here at b, the value of the function is f of b. So it's got to connect this point right here to this point right here. And we'll say that this is our value. How about that's our value of k? Right? So there's the horizontal line. It's got to pass through, right? Under what circumstances could it pass through at x equals a? Anybody got any ideas here? It's quite a conundrum. I'll give you a hint. It has to do with what kind of animal f is, what kind of mathematical creature it is. If it's one type of creature, go ahead, Caleb, what do you think? Okay, but now look at our criteria. F is continuous on the closed interval. So I got to be able to, the rules are, I've got to be able to put my pen down on the board at that point and pick my pen off the board at that point. And we're trying to decide where could the values of x be where I cross the function or where I cross the horizontal line. I told you last time that it really makes more sense for us to think about this as an open interval. And that's true, unless we allow f to be some kind of creature that we don't normally deal with. What do you think? And you kind of fill in the blanks. If f is creature A, then it can only intersect the line in between A and B. If f is a different kind of creature, then it could intersect at A or B. What do you think? Do you see what I'm getting at here? I mean, just think about this logically. If I put my pen down, we'll graph this thing in blue. If I'm putting my pen down right there at the point A, f of A, how could I cross K at A? What's the only way I could do that? Because Well, I don't know. What do you think? It'd have to be, right. Those points would have to line up vertically, wouldn't they? Right? It wouldn't necessarily have to be a vertical line, but it would have to at least do something like that, wouldn't it? Right? Well, what's unique about blue there, about that blue graph? That's not the kind of thing, it's not a function, right? The only way that it could cross at A or at B, if f of A and f of B are not equal to K, which it says they're not, right? K is the number between f of A and f of B. So K is not equal to f of A or f of B. The only way that it could cross K at A or B is if f is a non-function. Everybody get that? If f is a function, let's graph a function in green. Well, if it's a function, so it does not violate, there is no way that I could cross at A or at B. I would only be able to cross at values in between A and B. You see the point? Did they define f as a function? No, they didn't. They didn't. They just defined f as continuous, right? Didn't say it was a function. So if we go by that definition, then yeah, it could happen at the endpoints. Is that a useful definition? I don't think so. I think we typically are going to deal with functions, and so usually we would, if we restrict f to be a function, then that would turn into, right? If we restrict f to be a function, then it would be on the interior. Those would be the values guaranteed by the intermediate value theorem. Make sense? Okay, just a little, I just want to point that out. All right, so let's talk kinematics for a second. So we're talking physics here, and physics is a great way to illustrate the concepts of calculus. And I'm a physics student before I'm a math student, but physics involves so darn much math that I became kind of a math student. So kinematics is the study of motion, right? It's just in physics, it's when you guys take your physics classes here at the high school, that's where you'll start, is with kinematics. You have to really understand how to describe motion in order to understand what causes motion, right? So our kinematic quantities that we use are typically, we think of them as being position, velocity, acceleration, and then the parameter that's common to all of those functions. So the input variable is going to be t. Right? We're going to track the motion of some object with time, and we're going to describe that motion based on these three types of quantities. Okay? So let's start off just telling a story with graphs. Okay, now this story, you're going to have to just sort of imagine this, because it's a lot better if you're in the classroom and you can, well, I'll tell you what, maybe I could do that. Here, hang on a second. So I'm going to, let's see here. Okay, what if I do this? What if I go... So you can kind of see the front of the room there a little bit. Can I zoom that thing out, maybe? Okay, what are you guys seeing now? Do you see? I can't see what you're seeing. How am I going to do this? Mr. A, the camera's off. Oh, the camera's off? Oh, there you go. That's the problem, huh? This may not be worth doing. Okay, this is not going to be great, but you'll get the idea, right? So here I am up at the front of the room. We're going to say that this is the starting line. I'm just going to be walking in a line along the front of the room. So that direction is going to be, for you guys, that's going to be the positive x direction, right? That's the positive direction for my motion. And that direction is the negative direction. And this is going to be 0, right? Here, maybe I'll do it. Maybe it's better if I can get a little further away. Yeah, that's a little better. Okay, so here's 0. That's the positive direction. That's the negative direction. Let's tell this story. So I'm gonna snap my fingers, or I'll say go, when we're gonna start our study of the motion. Think about this as being like a video camera, right? And we're gonna start the video camera when I say go, and we're gonna stop it when I say stop. And the part of the video between start and stop is what we're gonna analyze. So here's the motion. Okay, ready? Start. Stop. Pretty boring. Okay. I'm walking in the positive direction, positive x direction, with constant speed, right? Okay, let's go up to the board and let's try to describe that. Okay, what's that going to look like? So on my graph, let's say that we're going to let's let this point right there be at x equals 0, right? So that's the place that lined up with like the pencil sharpener when I did my walk, right? What does it look like? What does my position graph look like then? What do you think? Any suggestions? I started off to the left of the 0 line, didn't I? Give me thumbs up on that. That makes sense? Okay, I ended up, after whatever it was, like 2 seconds, I ended up to the right of the pencil sharpener. So I ended up at some positive position, right? So what's that going to look like on my graph up here? Here's where we started. When t, here's my t-axis, when t is 0 right here, where should I be on the vertical axis, which is position, positive or negative? Somebody just shout it out. I don't think so. Wasn't I negative? Didn't I start off I started off negative, right? And then right in the middle, I was at 0, agreed? And then at the end, I was at some positive value, wasn't I? I had some positive value out here at the end after 2. So let's say this is after 1 second, that's 0 seconds, and that's like 2 seconds, right? So out here, I was up at some positive value. Well, if I connect those, I just get a line like that. Does that make sense? That's like my transition in time from my negative position to my positive position, right? Now, we have a really high quality video camera here, and so it's got an infinite number of frames between -1 or between 0 and 2 seconds, right? If I look at any one of those frames, those infinite frames, each one of those infinite frames is going to correspond to one point on that line, agreed? So if I pick this frame at t equals whatever, 0.679431 seconds, well, that's going to be my position right there, right? The y coordinate of that point gives me my position at that time. Does everybody agree? So that's the kinematic diagram. That's my position versus time graph that describes that really fascinating story I just told with my video, right? Walking across the room. Everybody agree? Okay. What if we were to look at my speed versus time? What would that look like? Now, I'm not going to, actually, I don't want to use the word speed. I'm going to use the word velocity. Okay. Because I know some of this is going to be a little bit hard to grapple with because you've never talked about this stuff before. But we have to distinguish really quick between vector and scalar quantities. And this is, I don't want to overload you. And this is not like, is this critical to understanding the calculus? No, you don't have to understand every nuance of this, but it's the better you understand the physics, the more realistic the calculus becomes. So you guys have talked about this maybe or not? I don't know. You tell me. Have you ever talked about the difference between a vector and a scalar?
Mr. Cooper went over it in physics, but other than that, I don't remember.
Okay, there's two different kinds of quantities. There are scalar quantities, and there are vector quantities. Scalar quantities, all they require, there's only one thing that they require, and that is a magnitude or a number. Vector quantities, however, require two parts. They require a magnitude, which is a number. And they require a direction. So an example of a scalar quantity would be something like the temperature of the room. Right, so if I walked over to the thermometer and I read that the temperature is 71 degrees, I don't need to know a direction with that. 71 summarizes that perfectly, right? Your progress through a novel, that's a scalar quantity. If you tell me you're on page 320, well then that's all I need to know, right? What about speed? Is speed a scalar or a vector? Say you're driving in your car, where would you look to find your speed? Where would you look to find your speed in a car? I'd look at the speedometer, sure. Does the speedometer change? If I've got my cruise control on, does the speedometer change as I change the direction of the car? No, it stays the same, doesn't it? So speed is another example of a scalar. Okay, well, what's a vector? Well, vectors are things where direction is important. So if we go back to, this is going to get kind of hard to do with going back and forth, but we'll make it work. So I'm going to go back to my story again. So I can only walk on this line right here. This is one-dimensional motion. So right now, if this is 0, where am I at right now? Assuming we're measuring it in meters, and that's 1 meter. What's my position right now? Say it loud.
1.
No?
12.
Okay, let me ask you this. What's my position now? I'm 1 meter away from the starting line, from 0. You might say, okay, so you might say 1. So then what's my position now? Well, you might say 1, but those are different places, aren't they? Right? I'm not standing in the same place when I am 1 meter away from the starting line here as compared to 1 meter away from the starting line here, am I? Those are different places. Agreed? They're different positions. Would everybody just, I can't see anything, so you just tell me yes or no. Would everybody agree that those are different positions?
Yes.
They are, right? Those are different positions. So the direction must be important here in this case. There must be a directionality. Either I'm going to be this side of 0 or I'm going to be that side of 0. Well, what's the most convenient way to distinguish those two different places? What do you suppose, if I'm going to call this a position of positive 1, what do you think I'm going to call this position then? Negative 1, right? So position is a vector quantity. It could be positive or negative, for example. Now, what about distance? If I ask you, let's talk about distance for just a second. If I ask you, how far did you run today? Let's say I ask you how far you ran, and Julia tells me she went out for a 5-mile run today. Is the direction important there? No, doesn't matter. She could have run a bunch of different places, right? But she ran 5 miles. That's a distance. Distance is a scalar quantity. It does not depend on direction, right? So if I want to know what's my distance from 0, well, it's 1 here and it's 1 here. That's a scalar, right? That does not include a direction. But if I want to know my position is a vector quantity because either it's positive 1 here or it's negative 1 here. Now, that would get much more complicated if I wasn't moving in just a straight line. If I were moving in 3 dimensions, I would have to have a way to identify a position in space. I'd have to have, that gets more complicated. Then I've got to have an X component and a Y component and a Z component that all work together to describe my position. But we don't want to get complicated like that. We're just going to move in a line for now. So it's very simple. We either have a positive position or we have a negative position. And so we don't confuse the two, right? Okay, so everybody really quickly, give me a 1 to 5 on that so far. I got to know how we're doing on this. Okay. All right, so then velocity for now. I don't want to get into, we'll come back and we'll address this issue of velocity again later, but for now we're just going to think about velocity as being a vector quantity. Okay, velocity is a vector quantity where the number part of the quantity is my speed, but the position part is it gives me a directionality, right? So if I'm walking along, let's say I'm covering 1 meter every second in this direction, what's my velocity? Well, the number part is 1 meter per second, right? That's the magnitude of my velocity. But if I'm moving in that direction, is the velocity positive or negative? What do you think? It's positive, right? But there's a difference between a velocity of positive 1 meters per second, which looks like this, and a velocity of negative 1 meters per second, which looks like this, because they're different directions, right? Okay, so we're starting to maybe, and when we come back later, when we have a little more calculus under our belts, we can add a lot more detail to this discussion. But I'm just trying to introduce these quantities that are going to be useful to us. Okay, so let's go back to our picture up here then. Okay, so here's our graph of position versus time, right? My position smoothly changed from -1 to +1 in 2 seconds. What if I wanted to tell that same fascinating story with a velocity time graph? What would it look like? And then just picture in your mind that really fascinating journey, that 2-second video of me walking in the positive X direction at a constant speed of 1 meter per second. What's my velocity?
Wouldn't it just be a constant value?
Yeah, it'd be a constant value of like 1, right? So wherever 1 is on this axis up here, let's say that that's 1 right there. It's just going to look like that, right? Just a flat horizontal line. Everybody see that? Okay. If I want to move these things together here, let me see if I can do this. Hope this goes the way I thought it was going to go. We'll see. Oh, it's not. Oh, man, come on. Let's try it again here. Oh, I know why it's doing it. There we go. Okay. There. If I overlap these two things, we can see the relationships at the same time then. How do we connect those two pictures? How are they related? How is the red graph related to the blue graph? There's a connection there. Yeah, right? The slope of the blue graph is equal to the value of the red graph, isn't it? Everybody see that? Okay, why would that be the case? Well, think about, see if I can undo that now. There we go. Think about what are the units going to be? Let's just look at this in terms of like a dimensional analysis for a second. We're going to measure position in meters, right? And we're measuring time in seconds. Okay, so if I look at a slope of this line right here, if I'm going to define slope for the blue line, slope is always equal to rise over run, isn't it? Normally it'd be delta y over delta x, agreed? Well, what's it going to be here? What's my rise this time? I don't have a y for my vertical axis. I have an x, right? So my slope is going to look like change in x, which is position, over, instead of a delta x on the horizontal axis, I've got a delta t, right? So that's my rise over my run. What does that sound like? Change in position. So that's going to be my change in position is how many meters did I change divided by how many seconds did I change. Well, that looks an awful lot like a speed or a velocity, doesn't it? Right? Everybody see that? So yeah, the slope of the blue line gives us the value of the red line, doesn't it? Right? Okay. Let's see if we can extend that definition. Okay, if I go back a page to these kinematic quantities, well, velocity, we can see right here, right? Velocity is the change in x over change in t. That's going to be the slope of the position function. What about acceleration? What do you think the relationship is between acceleration and velocity? What do you think the acceleration graph would look like here? Acceleration, we're all familiar with what acceleration feels like, but can we define it, right? So if we...
Be just a constant value at 0?
Yeah, because am I accelerating? What is acceleration? When do you experience acceleration? If you're driving in your car along a straight road, you only feel the acceleration when you're speeding up or you're slowing down, right? Otherwise, you don't feel any acceleration. So acceleration is what we associate with a change in velocity, and the relationship between velocity and acceleration is identical to the relationship between position and velocity, right? So velocity is going to be the slope of a position time graph, right? Delta x over delta t, rise over run. Well, look at this. Acceleration is the slope of a velocity time graph. Okay, so if we go back and we look at the velocity time graph, well, that just has a slope of 0 the whole way. And so the acceleration here is equal to 0. Okay, are you starting to put this together a little bit, these connections between these kinematic quantities? Let's try another story. Okay, let's try a more complicated story this time. How about one like this? Are you guys seeing? You're seeing the room, right? Okay, so here's my new story. I'm starting at, this time I'm going to start at the starting line. Yeah, I'll start at the starting line. Okay, which is at the pencil sharpener. And I'm starting from rest. Okay, when I say go, we're starting the video camera. Okay, ready, go. And then I start running. I'm just going to pick up speed the whole time. Okay, that's my picture. All right, there's the video that we just took. Let's describe that. Let's draw all the kinematic graphs that go with that one. Okay, what do you think the position time graph might look like? And let's see, get some other people contributing. I don't care if it's right, but I just want to know, what do you think it might look like? Let's take a couple key points maybe. I started off, I was at rest at the starting line, right? So wouldn't that be a point right here? right? And as I moved to the right, I was picking up speed. Andy, what do you think that graph's going to end up looking like then?
Would it be like a parabola?
Okay, yeah, parabola. So it's starting flat, and it's picking up speed like that. Everybody agree? Okay. Now, what about the velocity graph then? Andrew, what do you think the velocity graph is going to look like? If I'm, and I'll tell you, let's assume I was picking up speed uniformly. Go ahead, say it. It's linear, okay. So it's going to look maybe, I start with a speed of what? With a velocity of what? 0. And I end up with a velocity of whatever. After 2 seconds, say I'm going 2 meters per second, okay? So maybe that looks like that. Do that again. That's not very straight. Okay, something like that. So what do you think, Caleb, the acceleration looks like then?
I have no idea.
Okay, if I was uniformly picking up speed or increasing my velocity, what's our relationship going to be here? We said that, didn't we look at the slopes? Right, let's make this comparison here for a second between the slope of the blue graph and the value of the red graph. Right, if I were going to look at at like the slope of this curve here, that's a weird concept, right? What's the slope look like down here? Well, it's pretty small, isn't it? Right, if we think about an ant walking along this function, that's not a very steep hill, but the hill is getting steeper as we go, isn't it? So that's the concept we want to by the end of the day, that's what I just hope to be able to make a familiar idea to you, something that resonates and makes sense. As the slope of this thing increases, the value of the velocity function increases. Well, what's the slope? Describe the slope of the velocity function. What is it? I mean, we don't know what the number is necessarily, but how would you describe that? What do you think? Daisy, how would you describe the slope of that red line? Is it positive? Is it negative? Is it changing? Is it constant? What do you think?
I don't know. Looks positive.
It's positive for sure. Is it changing or is it constant? It's supposed to be. Ignore my crappy drawing, but it's supposed to be constant, right? So it's positive and constant. And so then what do you think the acceleration graph should look like, right? We said that the value of the velocity corresponds to the slope of the position. The value of acceleration then corresponds to the slope of velocity, right? If the slope is positive and constant, what's my green acceleration graph going to look like here, David? Positive and constant. Exactly. It's positive and constant. So it might just look something like this. Right? Well, I guess I don't go that far. It stopped right there, maybe. Right? Get the idea? Okay. All right. We'll come back to this. We'll come back to this in a little bit, but I want to define something for you now. We'll get back to our kinematics discussion. Just in general, we say in math that a secant line is a line that intersects a curve in two places locally. It might incidentally intersect the curve in other places also, but let's say that we know we have a function that has a value of x, f of x, and it has a value of x plus delta x, f of x plus delta x, if we move to the right by delta x. Okay, everybody see that? So there's my x value, there's the value of the function at x, and if we scoot to the right of our original x value by some amount we're going to call delta x, then this x value right here, right, if I want to write these on the graph, here's an x value of x, and then if that's delta x, this is an x value of x plus delta x. Remember, delta just means change in. So here's x plus whatever the change in x was. So that means that the y value here is whatever I get when I plug that into my function. So it's just f of x plus delta x, right? Okay, well, the secant line is intersecting the curve in places. if I draw a line through those two intersections, what do you think the slope is telling me of that line? Right? Slope is just rise over run. So the slope between this intersection, we could call delta y, or the change in the function, right? We'll just call it delta y for rise. The change in x, we already called delta x. So we can see then that the slope of the secant line is just equal to delta y over delta x. Well, delta y over delta x, that's just going to be this y value, which is f of x plus delta x, minus this y value, which is f of x, divided by delta x. That's what we call the difference quotient, and that's how we define the slope of a secant line. What's it telling me, though, for this function? What's the slope of that secant line telling me about the behavior of the function between x and x plus delta x? Can anybody describe that? How could we use some math words to describe what that's doing? Right? I'm going to throw some at you here, see if this makes sense. The slope of that secant line is telling us what the average rate of change of the function is on that interval, right? It's telling us how much did the function change compared to how much did the x change, right? So the slope of a secant line we always associate with what we call an average rate of change. This is not a calculus concept, right? This is a pre-calculus concept. We don't need any calculus. No, we haven't even really learned any calculus. We don't need any calculus to understand this. It can be really useful. Here's an example. How long does it take a car traveling with an average speed of 60 miles per hour to travel 150 miles? Well, everybody do that one in your head. How long does it take a car traveling with an average speed of 60 miles per hour to travel 150 miles? What do you think? Anybody got an answer? Amber, you said something. What's your answer? Yeah, how'd you get that?
I just divided 150 by 60.
Okay, good. So let's go ahead and make a picture, kinematic picture describing that. How about? Okay. How much time we got? Man, I really want to get through. I wish our classes were a little longer. Oh, okay. This is where we're going to probably have to end up, but. So if this is position, let's say we're traveling in a straight line. We're in the Midwest and we're traveling in a straight line the whole way. So we got x versus t. We know that we're starting off here at the starting line. And after 2.5 hours, so there's 1, 2, 3. So after 2.5 hours, we're going to be this far away. That distance right there is 150, right? So we're going to go from this point to that point. Everybody agree? Okay, so what does this description here says if the average speed is 60 miles per hour, then we're going to get from here to here, and the input value is 2.5. Okay, so what does that look like? Well, it could look like cruise control the whole way, couldn't it? Cruise control on 60. And what's the slope of that line? 150 divided by 2.5. That's going to be 60, isn't it? Right? That's my slope. Does it have to look like that, though? Did I have to have my cruise on the whole way? No, not really, right? Couldn't I have done this? Maybe I just accelerated really slowly the whole time. Maybe I started off at 0 and I gradually picked up speed the entire 2.5 hours, and I was going my fastest when I got to my finish line. Everybody agree? I still end up connecting the same 2 points on my position time graph. But my speed, right? Wouldn't you agree on my speedometer? It's got a low value there, it's got a medium value there, and it's got a really high value there. But the average rate of change here is the slope of this secant line. So the slope of this blue line that's connecting those 2 points is giving me my average speed. Is it telling me that that's exactly the speed I'm going the whole way? Absolutely not. In fact, it could be much more complicated. Maybe I'm doing something like this where I pick up speed and I lose speed and I pick up speed and then I stop there for a while so my position doesn't change and then accelerate to the end, right? It could do all kinds of things. But once again, as long as I'm connecting those 2 endpoints, the slope of the secant line is telling me my average speed for the trip, okay? All right, so let's consider the case here of what if we have a planet with no atmosphere and we're going to drop, so it's a rocky planet with a surface, and I'm going to drop an object from some height on that planet. What is the position time graph going to look like, first of all? What do you think? Isaac, what do you think the position time graph is going to look like? If I'm starting off, well, you know what the starting position is, right? So this time it's vertical movement, but it's still movement in a line, right? I'm just dropping an object and it's falling vertically from some high value.
It should be like constant straight line, like diagonal slope down, right?
Okay, so after some time, the position's going to be 0. So I've got to connect those 2 points, let's say. Okay, so is it going to do, Isaac's suggestion is it's going to do this. Is that what happened? Well, the Earth is an example of a rocky planet. If I drop an object off of, say you drop an object off of your house, does its position change uniformly? So for example, let's say you drop an object, just imagine this, you have to kind of use your imagination. Say we drop an object that's coated with sliprium, and that's a really expensive product. But we can coat an object with that and there's no resistance at all. You get it at the Acme store, extremely expensive, but we'll eliminate all air resistance, right? If we coat this thing up with sliprium. So we drop this thing and it falls for 4 seconds off this building. After 2 seconds, do you think it's gone half the way to the ground? Yes or no? Give me thumbs up, thumbs down. Thumbs down, yeah. Because when is it going to be traveling the fastest? At the start or the end of its journey? Okay, I'm seeing at the end, right? So this would imply here that when we're halfway to the ground, it's taken half the time. So I'm not buying it. That's not consistent with what we see on Earth, right? So I want a different answer for that one. There we go. So we're starting here and we're ending here, but what's the path going to look like? What do you think, Johan?
Wouldn't it be like a curve?
Okay, so it's starting steep or it's starting flat? Flat, right? Because it's starting, as time progresses, it's not changing its position very much, is it? Right? It's just doing something like that and it's picking up speed and now it's starting to cover more ground per increment of time. Does that make sense? So if we're looking at position versus time, that's what maybe it looks like. Everybody agree? Well, let's change this though. How about if we're measuring, okay, just to be consistent with my next slide, let's say that we're measuring the distance that it's fallen from you, right? You're dropping it from the building, and so the distance is increasing. So in that case, maybe it actually looks like that, right? It hasn't fallen very far at all, but after a while, it's fallen a long ways from you at the top of the building. So we're measuring distance it's fallen from your perspective. Make sense? Okay. What if we want to measure let's put some teeth to this and let's ask ourselves, okay, what if we want to find, we'll actually pretend we have a function. what if I want to find the average velocity of this object between 2 and 5 seconds? What could I do? So I've got this function that I could graph, right? And I'll pull up Desmos. And I know I have this on Desmos somewhere. Yeah, there it is. Okay. So this is my position function now. Okay. This is how far it's moved in a line as a function of time. Right? So there's my position function. This is S is on the vertical axis and T is on the horizontal axis, right? And we're really only interested between 2 seconds and 5 seconds, right? So we're interested in that point. After 2 seconds, the object has a position of 1. And we're interested in this point. After 5 seconds, it has a position of 8.5. If I want to know the average velocity of the particle, I just want to know the slope of the line connecting those two things, right? Okay, well, that's just this line. Nope, not there. It's that line right there, isn't it? There's my secant line. Okay, what's the slope of that line? Well, that's just going to be, rise over run. So it's going to be 8.5 minus 1, which is 7.5 meters, divided by 5 minus 2 is 3. 7.5 divided by 3 is 2.5, or 5 halves, right? That's my average rate of change. Everybody agree? Okay, to find that, do I have to have a graph? No, I don't need a graph. I could just do this, right? If I want to know the average velocity is just going to be S of 5 minus S of 2 divided by 5 minus 2, right? Because isn't that just equal to S of t plus delta t minus S of t over delta t? Okay, we'll wrap this up next time. This stuff takes a while. Give me a 1 to 5 real quick though. Is it starting to make a little sense? Okay, and if you're 3 or above, I'm pretty darn happy about that, honestly. I mean, this is some pretty big concepts. All right, we'll hit it next time. Have a great day.